Welcome back to the session on statistical inference part 1. In the earlier part of this session, we have seen conceptually what do we try to do or accomplish in statistical inference. We tried to understand some terminologies like hypothesis, level of significance, type 1 error, type 2 error and power of the test. After formulating the hypothesis, we have to conduct a statistical test. So, just to set up the link, I consider this example once again. We had formulated the hypothesis for these increased alkaline phosphate levels. It is mu equal to 60 versus mu greater than 60. This is a one sample test, that is why we are checking whether the average population value is equal to 60 or greater than 60. Now you will tell me that this is a one-tail test. We have seen that there are either one-tail test or two-tail test. One-tail test implies one direction under the alternative hypothesis, whereas two-tail test indicates the both directions in the alternative hypothesis. So, if you write this as mu not equal to 60, then it becomes a two-tail test. We are considering that mu greater than 60. So, we are sure that either this H0 is true or H1 is true. There cannot be anything else as being true. So, what to do next? We have formulated the hypothesis. So, in general, any statistical test procedure follows the following steps. Formulate the null and alternative hypothesis. Fix the level of significance, which is the probability of type 1 error. We know that the probability of type 1 error we consider and fix at level alpha, because the type 1 error is considered to be more serious than type 2 error, and 1 minus probability of type 2 error is the power of the test. So, we fix the level of significance alpha and try to maximize the power. Having done that, determine the sample size n. Now, you can determine the sample size n by considering various aspects. One of the aspects of determining sample size is use the value of the power. So, how much powerful you want your test to be? What do you want your power of the test to be? Do you want it to be 90% powerful? So, you will consider power equal to 0.9, or you want it more powerful, so then it is 0.95 and so on and so forth. The power of the test is a function of sample size n for fixed value of alpha. We have seen that alpha and beta are conflicting in nature, so obviously alpha and power are also conflicting in nature. But having fixed alpha, now we are talking once we have fixed the value of alpha. So then the power becomes as a function of sample size n. It can be a function of delta also, which is the difference to detect. We will not go into the details of determination of this sample size. One way or the other, you determine the sample size n. You take a sample of size n. That means you observe these n patients in your clinical trial. Record the observations on these patients. We generally denote them by x1, x2, xn, and then compute a test statistics. So, this is a key thing in any statistical inference test. You have to compute some test statistic. On the basis of this test statistic, you come up with some test rule which tells you when to reject H0 and when to accept H0. So these are the steps one has to follow. Let us see how will we come up with the test statistic for the example or illustration we are considering. We have formulated these two hypotheses. We have fixed the value of level of significance at 0.05. Suppose we have decided to take a sample of size 50. Then this is a test statistic which is a normal one sample test, assuming that the other parameter sigma as known of the normal distribution. Then you can compute the test statistic as Z, I am denoting as Z observed, equal to x bar minus mu naught divided by sigma upon root n, where x bar is the sample mean. You have observed the data, so you can calculate the value of your sample average. Mu naught is the hypothecated value, which is 60 here. You are specifying that we claim that mu is equal to 60. So if you say mu equal to 60, then this mu naught value is that value that we have considered here. Then divide by sigma upon root n. Divide by sigma upon root n. So having computed this value, you will get the value of the test statistic. Now, see, when will we say that our sample is really coming from the population with mean equal to mu naught if this difference x bar minus mu naught is sufficiently small. So if x bar is closer to mu naught, then we tend to accept this hypothesis. That is the fundamental logic or concept. So if the difference x bar minus mu naught is sufficiently small, then you will say that yes, mu should be equal to 60. But if x bar minus mu naught, the difference between the sample mean and the hypothecated value mu is large, then you will say that this cannot be true, but this will be true. Now, which is large and which is small, that is the question debated in statistical inference. So therefore, this is an objective rule posed that you compute this thing. So this is nothing but the standardized difference between the sample mean and the hypothecated value. So let us move further. So the test rule says reject H0. So reject H0 means accept H1. And what is accept H1? What is H1? That mu is greater than mu naught. So if this value of Z is greater than or equal to some critical value of the normal distribution, this is provided by statistical tables or by any software. So if Z is greater than something, so see, you wanted something which is should be objective, and that is based upon the value of alpha. So if the value, calculated value of Z is greater than or equal to the critical value of the normal distribution, then you reject H0 and you will conclude that mu is greater than 60. If it is not so, then you will accept the null hypothesis. So that is the test rule. There is another way of looking at the same thing through p-value. We had stopped at the concept of p-value because I thought that you should first know the procedure of conducting a statistical test. So either you can adopt this way or you can adopt this way, which is compute p-value as the p-value of probability that your Z distribution, normal distribution, greater than or equal to the calculated value of Z. So compute this p-value and reject H naught if p-value is less than 0.05, otherwise accept H naught. This is the statement. Even though you don't remember anything, remember this statement that having computed the p-value, SAS gives you the p-value of any test. So, and this is true for any test, statistical test. So if the p-value is less than 0.05 or the alpha that you have chosen, then you are going to reject H0 and you are going to accept H1. So most of the times you are going to declare that the drug is effective. If it is greater than or equal to 0.05, then you are going to accept H0, or you will say that the difference is not significant. Difference is between what? Difference between the value of mu and mu naught is not significant, or your sample is not able to reject the hypothesis H0. Statisticians are reluctant to call this as accept H0, but they say that we fail to reject H0. But we will not go into those philosophical details. We will just say that if not so, then just accept H0. That means you are into the null hypothesis situation. So, what is this p-value? The p-value is the actual probability of obtaining the calculated test statistic or a value in a more extreme part of the rejection region when H0 is true. I would like to explain to you the meaning of p-value through this graph. Let us go and try to learn by heart these test rules. Okay. Let us not bother about acceptance. Let us just look at when do we reject H0. So reject H0 if your calculated value of Z, that is Z observed, is greater than or equal to the critical value given by the normal distribution. So this rule is the same as this rule. Reject H0 if p-value is less than 0.05. So the situation that your observed test statistic greater than or equal to the critical value is the same or is identical with the p-value being less than 0.05. So remember this, what I have told you now, and now look at this picture. See, Z alpha, this is the critical value given by the normal distribution. And what does it mean? Why are we calling it as a critical value of normal distribution? Because beyond this, this much area, that means we call it as right tailed. This area of this tail is equal to alpha. Okay. This is a normal distribution, which is the distribution of the test statistic under H0. We are not interested into those theoretical details right now. So basically, Z alpha is such point that beyond which the area, and area is nothing but probability, is equal to alpha. Now, you have computed the value of Z statistic, and that is Z observed, suppose. Now, suppose your Z observed falls here at this point, okay. Then what is the p-value? It is again the probability that you are beyond the Z observed. So this is reddish area will be the p-value in case of one-tailed test we are talking of. So here you will see that the p-value, this much area is less than this tail, So p-value is less than alpha. So p-value less than alpha, that means our Z calculated Z value is greater than Z alpha. So the two statements are similar, that if your Z observed test statistic is beyond the critical value, this is the same as saying that the p value is less than alpha. And in that case, you are going to reject H naught. Now, why are we going to reject H naught? Because we have considered that alpha will be our type 1 error. So, this we don't want it to cross. We want it to be this is the maximum probability that of type 1 error that we would like to commit when H naught is true. So, the p value is the actual probability of obtaining the calculated test statistic in a more extreme part of the rejection region. So, you are beyond that Z alpha. In order to understand further, let me get all the bullet points here. The smaller the p value is, the stronger the evidence against H naught provided by the data. Conventionally, the p value is compared with the level of significance alpha. If the p value is less than alpha, then H naught is rejected. This implies that the drug is effective as compared with the placebo in two sample situations. Alternatively, if p value is greater than or equal to alpha, then we fail to reject H naught. This implies that the drug is not superior to the placebo. The definition of p value or the interpretation is the probability computed assuming that H naught is true, that the observed outcome would take a value as extreme or more extreme than that actually observed is called the p value of the test. This is easier to understand. The p value indicates the amount of error that can exist if the researcher chooses to reject H naught on the basis of his sample. So, if anybody asks you the definition, you can as well give this, because it is similar to the definition of level of significance. So, it is the amount of error that can exist. So, on the basis of your data, if you decide to reject H naught, then how much error you are going to commit? You are going to commit the error equivalent to your p value. Okay. So, mechanically speaking, you will have some tests, you will have some hypothesis that will involve some test statistic. The SAS or any other software is going to give you the values of the test statistics, the standard errors and lot many output with the p value. You look at the p value, see what is the level of significance used, whether it is 5%, 10%, 1%, and compare the p value with your level of significance. If the p value is less than the level of significance, then you are going to reject the null hypothesis and accept the alternative hypothesis. Let us see some examples so that the things would be clearer, because we learn better from examples than just the concepts. Now I am considering a Z test, which Z is meant for normal test. Z test for two sample means. If you remember, in one of our sessions, I talked about the central limit theorem, that whatever may be the underlying distribution, if you are taking large samples from that distribution and computing the sample means, then under certain regularity conditions, the sample means follow normal distribution. So, this Z test for two sample means is meant for large samples. How large? Even if the sample size is greater than 30, you can use this Z test, that holds. Now, why it is called two sample? Because here I am considering that there is a treatment T and there is a control drug. So, we are interested in testing H naught, that the drug is effective or the drug is different from the placebo or control. So, H naught is, as we always formulate it, it is mu t equal to mu c. That means average response of the endpoint population, average population response of the endpoint for the treatment is the same as that of control. That is what the statement says. Versus the alternative hypothesis can be that the average response due to the treatment is not equal to the average response due to the control. Or if you are sure that your drug is going to increase the response, then you will formulate the hypothesis as mu t greater than mu c. If you are sure that the drug is meant for lowering something such as blood pressure, then you formulate the hypothesis as H1 mu t less than mu c. So, you will be in either of these situations. Okay, fine. Now, what will you do? You will take samples from the drug population. That means you will observe the responses of the patients who are administered the drug T. How many? You are assuming that you are giving the drug to NT people, you are giving the control to NC people, and you compute the sample means x bar T and x bar C, and then you can find out the standard error by using this formula. We have assumed that sigma is known. If sigma is unknown, then we cannot use the Z test, but we use the T test. We will see that situation also. This is an data which I had considered earlier also. Data of a survival study that include the survival times in months of 65 multiple myeloma patients with data on 15 concomitant variables. Here is the reference for that. I considered only the variable urea, and I want to see whether the average urea content in males and females is the same. So, my populations T and C are males and females. I have two populations and I am interested in seeing whether mu T is equal to mu C. Versus the alternative hypothesis is average urea content in males and females is not the same. I conducted this analysis using Microsoft Excel, and here is the output. The means are like this. So, this is mu T, this is mu C. So, mu T minus mu C comes out to be negative minus 3.83223. I could have said H1 that average urea content in males is less than that of females. But I have formulated the hypothesis as a two-tailed hypothesis by saying that it is not the same. But it gives all these p values. See, p z less than or equal to z, 1 tel, p z less than or equal to z, 2 tel. So, we have to consider this value. This is the p value we will focus on. Now, what is the p value? P value is 0.000127. Is it less than 0.05? Is it less than 0.05? Yes, this value is less than 0.05. So according to our rule, we will reject the null hypothesis. So what will we conclude? We will conclude that the average urea content in males and females is not the same. If you go by the Z rule, then the observed value of Z is this. Whenever you are into the two sample situation, then you have to take the absolute value of this Z statistic. It will be 3.83. So compare this 3.83 with the Z critical to tell. Okay. So what is happening? 3.83 is bigger than 1.96 or 1.95 here. So according to that test rule, also we will reject the hypothesis because Z observed is greater than the Z critical. Whenever we are into two-tailed test, then we have to consider the absolute value. So both ways they will be always consistent if you go by comparing the observed value of the test statistic with critical value, or through p-value you should get the same result. Okay. So that was the Z test, which is mainly used for the large sample test. Whenever our sample sizes are small, that is suppose less than 30, then you have the same hypothesis here, mu1 is equal to mu2 versus mu1 not equal to mu2. The test statistic is this, y1 bar minus y2 bar. So here if you remember, this sigma square is replaced by some S square P, which is a sample quantity. So whenever the population parameter is unknown, then you try to estimate it from the sample. And just like normal distribution, there is some statistical distribution known as T distribution, which is also famous as students T distribution. So this decision rule is reject H naught if absolute value of T is greater than the T alpha by 2 n minus 1 etc. Now what is this? This is nothing but the critical value provided by the T distribution. So the test statistic T is a function of this difference standardized by its standard error, namely so and so forth. Large values of T will lead to rejection of the null hypothesis. When H naught is true, T has the student's T distribution with n minus 2 degrees of freedom where n is equal to n1 plus n2. That is n1 plus n2 minus 2 degrees of freedom. You need not remember all these technicalities. Try to understand conceptually that you are finding out something as standardized difference between the two, y1 bar minus y2 bar, which are your sample means. If they are quite closer, then you will say that mu1 is equal to mu2. If they are far apart, then you are going to say mu1 not equal to mu2. That's it. What is going to determine whether they are closer or far apart? This critical value from the T distribution. So, let us consider an example. A new compound ABC123 is being developed for long-term treatment of patients with chronic asthma. Asthmatic patients were enrolled in a double-blind study and randomized to receive daily oral doses of ABC123 or a placebo for 6 weeks. The primary measurement of interest is the resting FEV1, which means forced expiratory volume during the first second of expiration, which is measured before and the end of the 6-week treatment period. Data in liters are shown in the table which follows. Does administration of ABC123 appear to have any effect on FEV1? So this is the question we are addressing. So there is some measure FEV1, you have measured it baseline and after 6 weeks, and this is for the drug group, this is for the placebo group. Clear? What you are interested in, you are interested in the change. So you compute whatever you have measured after 6 weeks and what was initially. So this is the variable you are interested in, change. And then you run the proc means by treatment group because you want it for both, and then you can get the summary of the descriptive statistics for both these treatments ABC 1 to 3 and the control, and this is the proc of t-test. So proc t-test data is equal to FEV, class treatment group, variance, variable is change, and you run this program, you will get the output like this. This is treatment group up to this. So there are 11 patients in having the drug ABC 1 to 3. The remaining are getting placebo. The change in the volume is specified in this column, change, and then we are interested in seeing whether this particular block for ABC 1 to 3 is significantly different from the block for placebo. This is the means procedure giving the descriptive statistics, mean, standard deviation, n, and t value, probability greater than t, and treatment group placebo is giving this value FEV0 and change, but we are interested in mainly the value of the change. So here the t value is t.3.21 with, this is nothing but the p value 0.0094 and this is the p value 0.1107. That was for single sample. When you used the t-test using the equal variance, see, the t-test can be used with the assumption of equal variances between the two groups or unequal variances between the two groups. So if you assume equal variances, then it gives you the p value as 0.3425, and if you assume unequal variances, then it gives you the value of 0.3420. And let us see the interpretation. The SAS code for analyzing this data set computes the pre to post study changes in FEV1 and then prints a listing of data by using proc print. Proc means is used in this example to obtain the summary statistics for the baseline and week 6 response values for each group. The T and PRT options are specified in the proc mean statement to illustrate the one sample t-test for the significance of the within group changes. We are actually not interested in this output. We are interested in the comparison. So actually our interest lies in this particular output. The two sample t-test is carried out by using proc t-test with the class variable treatment group specified in the class statement. Assuming equal variances, you use the t value and p value, which is probability greater than mod t, corresponding to equal under the variances column. So as we were looking at the SAS output, the value of the t statistic was 0.97 and the p value was 0.3425. So what does that indicate? Since it is bigger than 0.05, it indicates that there is no significant difference in the FEV1 increases between the two groups. So, this ABC 1, 2, 3 is not doing anything different, I would say, because we are talking about the two-tailed test. Anything different from that of the placebo. It also gives you the value of F statistic, which is used for equality of the variances, sigma 1 square equal to sigma 2 square. So, which leads to the non-rejection of the null hypothesis of equal variances. So, basically you can also test for equal variances, and since it gives you the rejection, you should be using the p-value of the unequal variances t-test, that is the Satterthwaite t-test. So, as noted in the output, the p-value associated with this preliminary test is 0.9532, which is known as Satterthwaite's t-value, and with some degrees of freedom. Degrees of freedom is a parameter for the t distribution. So, in both the cases, it indicated that the drug is behaving no different than the placebo. I have tried to cover the two sample scenarios. So, the first test we talked about was the Z test, which is meant for equality of means, large samples. Then the T test, equality of means for two samples, that is drug versus control for small samples. And now, if the response is of binary type, it results into either success or failure. In our initial sessions, we have talked about different types of endpoints. Binary endpoint, whether the patient is discharged or not discharged, whether a tumor is formed, not formed. So, this kind of situation, then we use the chi-square test, and there we are not talking about the means, but we are talking about the binomial proportions. So, in the analysis of clinical data, the binomial proportion typically represents a response rate or a cure rate or survival rate, abnormality rate, or some other event rate. So, something happens or something does not happen, and we are trying to see whether that something happens or does not happen is same for treatment as well as for control. The chi-square test is an approximate test which may be used when the normal approximation to the binomial distribution is valid, that is for the large samples. You have a 2 by 2 table like this, that this is group 1 and x1 are responding for this group, from this group 1. So, group 1 can be treatment, group 2 can be the control. So, x1 are responding and here x2 are responding. Then the number of non-responders from group 1, that is from treatment group, is say n1 minus x1, and from group 2 is n2 minus x2. So, if you are having that 2 by 2 table, then you can calculate these numerators and denominators and the test statistic as chi-square as numerator square divided by denominator. So, the null hypothesis is P1 equal to P2 versus H1, P1 not equal to P2, and again as before you will reject your null hypothesis if the calculated value of the test statistic. This is a famous letter called chi. It is written as CHI like this, but its pronunciation is chi. So, chi-square, we call it as chi-square. Do not get bogged down by the notation. This is something that we compute. If that something is greater than the critical value, you are going to reject the H0. And what is this chi-square 1 alpha? This is the critical value by the given by the chi-square distribution. just as we had the critical value from the t distribution. Since you people are going to use the software like SAS, you don't have to compute the test statistic and p-value, etc. What you have to do is that whatever the output is given by the SAS procedure, you should be able to interpret it in a proper manner. So, even though you feel that this seems to be quite complicated, this is explained to you for the sake of completeness, because once you understand what it is being done in test statistic and what is the p-value, then you will be able to interpret the SAS output in a nice manner. So, you don't have to remember or learn by heart the formulae here explained in all these slides. You can yourself also collect several data sets, or you may be having several data sets on which you can just use this proc t test or proc means with the options, and then you will be able to learn, try to interpret the output for your data, and then you will actually enjoy the inference part of it. So, let us consider one more example regarding this 2 by 2 chi-square test. A study was conducted to monitor the incidence of gastrointestinal adverse drug reactions of a new antibiotic used in lower respiratory tract infections. Two parallel groups were included in the study. One group consisted of 66 patients randomized to receive the new treatment, and a reference group of 52 patients randomized to receive the existing erythromycin treatment. There were 22 patients in the test group and 28 patients in the control group who reported one or more GI complaints. So, we are talking about the side effect, gastrointestinal adverse drug reaction. So, 22 out of 66 reported the adverse event, and 28 out of 52 reported the adverse event. Is there any evidence of a difference in the GI side effect rates between the two groups? So, that is the question we want to answer. So, what is response? Response is the event that a patient develops one or more GI reactions during the study. And obviously, we have to compute the proportions, the probabilities that a randomly selected LRT1 patient has such a response when treated with the test drug and the control drug respectively. The same data jotted down in a tabular form. 22 are respondents in test drug, 28 respondents in control, because there were 66 remaining were non-responders, and so on and so forth. You first enter the data, and then in proc-fric only you have this chi-square option available in SAS, which gives you the output. So, here the chi-square degrees of freedom 1 value is 5.0119, and with probability 0.0252. So, this is the p-value. This is the p-value. This is the value of the test statistic. Now, you will see several such outputs. So, they are more and more advancements or improvisation on the chi-square test. There is something called as likelihood ratio chi-square test, continuity adjusted chi-square test, Mantel-Hassell chi-square test, contingency coefficient, Cramer's V, phi coefficient, and what not. We are at a very elementary level, so we don't bother about the other outputs. We just go by the chi-square value and its corresponding p-value. Similarly, there is also something called as Fisher's exact test. So this is also one of the popular tests. The name exact suggests that here it is not using the normal approximation. It is using the exact distribution of the test statistic. So here also you are getting these p-values, left p-value and right p-value. See, whenever you are having pt less than pc, you will consider this. When you have pt greater than pc as your alternative hypothesis, you will consider this p-value, etc. So, the SAS code for conducting the chi-square test using proc-freq is shown next. The stable statement identifies the row and column variables that are used to form the 2 by 2 table. The wait statement specifies that the response variable CNT is read into the data set by SAS as cell frequencies. If the response data, yes or no, are input individually for each patient, the CNT variable is not used and the wait statement is omitted from proc-freq. These are all the detailing or different options of SAS procedures which you can, if you refer to the SAS help for that particular proc, you will come to know all these points. So, the value of the chi-square test statistic is 5.012 with a p-value of 0.0252. What does it signify? Since the p-value is less than 0.05, we are going to reject the null hypothesis. Similarly, the continuity corrected chi-square value is so and so and the p-value is 0.0403, which is also less than the 0.05 and therefore we reject the null hypothesis. So the proportion, if we reject the null hypothesis, what do we accept? Then we accept the alternative hypothesis. And what does alternative hypothesis say? The alternative hypothesis says in this case is that the proportions of developing the GI reactions in the two groups is not the same. They are different. We have learnt in the consecutive 2 sessions of statistical inference the concepts of hypothesis testing, then what are 1 and 2 tailed hypothesis tests, type 1 error, type 2 error, what is meant by power of a test, p-value, its interpretation and example, and then some examples on z-test for 2 sample means, 2 sample t-test and 2 by 2 chi-square test and example. Truly speaking, the statistical inference is such a vast subject that it is very difficult to capture it only in 2 hours. So, I would suggest that don't lose your heart if you don't understand the things in detail. Try to see what you require and whether you understand that much or not. Try to understand the concepts. Then the 3 tests, I have tried to choose the most popular tests, but there are thousands of statistical tests which you will come across. But the underlying concepts of these things remain the same.